Good morning to all of you. Today we all gathered here to celebrate the discovery of Raman effect. We believe that nuclear science and technology are critical tools for achieving sustainable development. Hence, to celebrate them, a role of nuclear science and technology, we have invited two esteemed guests. These are lighting on the accelerator, science and technologies. We welcome to the guest. For the welcome to the guest, I would like to invite my HOI and head, Dr. Alpna Goyal.
Welcome you, sir. Good morning to one and all present here. I am extremely delighted to welcome our two great Indian scientists to Amity University who have contributed immensely in the field of nuclear physics. On the behalf of Amity University management, especially our Honorable Founder President Dr. Ashok K. Chauhan, Chancellor Dr. Atul K. Chauhan, and Vice Chancellor Madam Dr. Balvinder Shukla, and my own personal behalf and my Amity Institute of Nuclear Science, this is my proud privilege. I welcome Dr. R.K. Bhandari sir and Professor S.C. Pancholi sir. Both are well-known nuclear physicists. Thank you, sir, for accepting our invitation. Today, we are celebrating National Science Day. On 28th February, India celebrates National Science Day every year to commemorate the discovery of Raman effect by the great Indian physicist, Shri C.V. Raman. He was awarded Nobel Prize in Physics in 1930. And that was the first who got Nobel Prize in Sciences from India. I would like to share with you that this year we are celebrating National Science Day as Global Science, Global Well-being. I would also like to welcome all students who joined us and also the faculty member from the Amity University and Nuclear Science and Technology who are here. I am sure you all will learn today a lot of physics and science phenomena, and we all will be benefited, and there are a lot to take away from their lecture and from their interaction. I would like to invite each of my students of nuclear science and technology, please interact with these. This is a great opportunity which you are getting. It's not possible to get them on the dais. It is very difficult to invite them. These people are very busy, and from their busy schedule, they find out the time for you. So I invite each my student, and also I request the guest, please bless our student so that they can become a good leader of India in nuclear science. With this word, I welcome each one of you, and I hand over to the dais to the sir, Professor A.K. Jain, to continue the program. Thank you.
All right. So, good afternoon to everybody. And thank you, Professor Alpna Goyal, for arranging such a nice program and inviting two of our distinguished scientists, Dr. R.K. Bhandari and Professor Suresh Pancholi. Both are very celebrated people in their own right. And you will see from their CV that somebody will present here. So I will just take few minutes to set the background. C.V. Raman, whose full name was Chandrasekharan Venkat Raman, he actually made this discovery in Kolkata. And he was not even working in science at that time. He started working just a little earlier to this discovery in his free time. He will go to the Indian Institute of Cultivation of Science and set up the lab himself and used to do his experiments in the free time. This was his interest. So it is remarkable that when he announced this discovery on 28th February 1928, he got the Nobel Prize within, I think, 1 or 2 years. Welcome. And he was so confident that he will get the Nobel Prize that he had already booked his tickets for the Nobel ceremony program beforehand. He was so sure this discovery is so important that it's going to get the Nobel Prize. So that tells us several things, you see. First of all, that you have to believe in what you are doing. You must always believe in what you are doing. Don't think that what you are doing is not meaningful or useful. You have to make it meaningful. And this is the equipment which is still preserved in that institute. If you ever get time to go there, it is displayed in their main lobby on the first floor. I saw it. And you can see C.V. Raman with this equipment, which he designed and built himself. He purchased every part from the local markets, go around and purchase it. See, he was not a Bengali. He was a South Indian living in Bengal. And he was able to manage that in those days when there is hardly anything available to do science in India. So these are some important traits of Raman, which make him very unique and special. So this spectrograph may have cost him maybe 200 rupees or something like that in those days. By using this, he made this discovery. The Raman effect is so wide nowadays in every area of science and every area of application of science into various fields. There are various kinds of applications. Raman effect and Raman spectroscopy is being used. And you can see several of them listed here, at least 4 of them. Resonance Raman spectroscopy, surface enhanced Raman spectroscopy, micro Raman spectroscopy, nonlinear Raman spectroscopic techniques. And with the arrival of lasers, it has further enhanced the impact of Raman effect. So these various techniques, they have applications in telecommunications, in nanotechnology, biology, medicine, remote sensing, mineral exploration, etc., etc. So many applications are there. which people could not imagine in those days. Now, what will be the role of nuclear science in present day scene? As Alpana Madam told, that this year's National Science Day theme is Global Science for Global Well-being. So science should be used for the well-being of the people. Whatever we do, it is a double-edged sword, particularly in nuclear science. It has both kinds of applications. It has got a tremendous destructive capability. It has got tremendous constructive capabilities also. How you use them. So, in the present day world, which is facing new challenges, there are a huge number of man-made disasters happening nowadays. Natural disasters, man-made disasters, both are having a lot of impact on our society. I was reading yesterday only in a news from UK, they don't have vegetables in the market now. So when they go to buy in the market tomatoes, so they have restricted, you will get 3 tomatoes per person, 2 potatoes per person. Can you imagine this situation? So this is because of the very unusual weather conditions in the countries which used to feed vegetables to UK or export to UK. They have all dried out, and UK is still away from its own production because in winter nothing grows there. So such situations are happening. Events like earthquake recently that happened in Turkey and Syria, and huge storms coming everywhere. These are affecting our life. See, things happen somewhere else, but they affect you also, because now the world is a global integrated thing. Never think that something happened, oh, hame kya karna hai, kuch nahi hoga. It's not like that. No longer like that. So, weather change is a reality that is causing huge sufferings. And in our neighborhood, Pakistan is reeling from huge shortage of food. It had faced huge floods in recent past. It wiped out all the crops completely. So, and we have passed through the COVID pandemic recently, and people are saying that such pandemics will be common now. So you can see the life is becoming more complex as the technology evolves. We have more resources, more means of doing new things, but life is becoming more and more complex also. So what nuclear techniques can do, because we are a nuclear science department, so I will just cite 3 basic examples where they are making a lot of contribution to the society. One is the proton and hadron therapy. Professor Bhandari will talk about accelerators. These are the tools for various kind of applications. And he is an accelerator expert. He was the director of the Variable Energy Cyclotron Center in Kolkata, our first big accelerator center. And proton and hadron therapy, they are being used to treat cancers which could not be treated earlier, for example, like brain tumors and other things. And there are stories, real stories, where patients have been treated in 2 or 3 days and gone home to work. Nothing happened. No radiation effect, nothing, because these techniques are very precise. In normal radiation therapy, your whole body burns. But with these techniques, you can burn only the tumor. They burn it, finish, go home, like taking out a tooth, putting a new one, go home. Use of radioisotopes and isomers is very common. You all know that 99 technetium is the most used isomer in the world. Almost 40 million doses are used, administered every year in the technetium 99. Similar to that, there are many other radioisotopes which are being used, and they are making huge contribution in not only medical treatment, also diagnostics. Then there are ultra precision clocks that we are expecting in future, which will be based on nuclear transitions. The present day atomic clocks, they have an accuracy of about 10⁻⁻17 seconds. We expect that the future nuclear clocks, they will be precise to the level of 10⁻⁻19 seconds or more. Now somebody will ask question, how does it matter? 2 0 और लगा दिए की होंदा, अरे क्या कर लेगा भाई, 2 0 और लगा दिए तो इससे क्या हो जाएगा? क्यों इतना परेशान हो रहा है कि नहीं, हमको तो अभी तो 17 0 लगे थे नीचे, अभी 2 और लगाने. The idea is that these clocks, precise clocks, they control your lives now. The whole GPS system, management of all the flights that are going around the world. Every country has its own GPS system for military and civilian use. They are all based on these clocks. And if the clocks are more precise, your usage becomes more and more precise. Right now, you have got a uncertainty or error of about 20 meters to 50 meters. It will come down to few centimeters. Now, this has a lot of applications. For example, one of the isomers on which the nuclear physicists are focusing nowadays is 229 thorium. It has got a very unique gamma transition of 8 kiloelectron volts, which is very rare in nuclei. Nuclei generally have transition of the order of hundreds of keV or million electron volts. This 8 keV transition is the first hope that people have in nuclear physics, where they can make nuclear lasers, and this can be used to produce nuclear clocks. And many of them are saying that we are very close to that. Several labs are working on that. And their whole work is just on this only. They work only on this, nothing else. So a precise knowledge of this excitation energy of 8 keV, which is known up to with a precision of only 0.17 keV plus minus, but they want this more precise because only then the tuning can be done. And this will lead to very ultra precise clocks, which will make the satellite-based navigation more precise. And it will be possible from satellites to observe the changes in the crust of the Earth beforehand, much before an earthquake comes. So it will be so precise. Then you can predict the earthquakes. There is no way to predict earthquakes so far. But if you can predict it even a few days before, that is going to be a great advancement in saving lives. So another application that is being looked at is because when earth tides come, seismic activity happens, weathers change, then there are changes in the gravity of the earth, local changes. They can be measured by using such clocks as gravity sensors. And this can become a very good predictor. You can make forecast of various atmospheric or other weather conditions more precisely. So these are just 3 examples that I have given, and I will not continue more than this. And with this, I will hand over the mic to Dr. Unnati Gupta here. She will introduce the speakers and let us listen to them. Thank you.
Thank you, sir, for taking away for the journey of Raman effect and other things which are involved in nuclear science and technology. Now we are going to start the program. For starting the program, I would like to invite today's panelist on the dais and Professor Jain as moderator of the program. Before I would start the program, I would like to tell small lines about, these are the literally small lines which I am talking about them. These are are larger than the life. What they have done in right area. So first I will start with the Professor Jain as a little bit few lines about him. No. All right, sir. So I would like to start with Professor R.K. Bhandari. So I'm not taking your too much time to explain his journey of life. The few lines are there. The Professor Bhandari presently he is honorary visiting scientist at the Inter University Accelerator Center, former director of Variable Energy Cyclotron Center, Kolkata, and a distinguished scientist DAE. He is also serving for several national and international bodies or committees related to the R&D projects and academics too. Apart from all these things, I would like to say that the most interesting project what he has done is he has devoted his 44 years of life for the cyclotrons. So if you would like to say call one who is the father of the cyclotron in the India, so now name comes of Professor Bhandari. So this is a larger than other things. No explanation is needed for the father of the cyclotron in India because his CV is too much large, too much long. So whole day I will take to tell about that. Some CV is also we have circulated to tell more details about the The our second guest is Professor Suresh Chand Pancholi. He is also devoted too many years or whole life, not the years, whole life to the Nuclear Society. So presently he is honorary visiting professor at the Inter-University Accelerator Center, a former professor, Department of Physics and Statistics, University of Delhi. The Professor Pancholi has a 30 years long career in the teaching and research. He has taught nuclear structure physics at the University of Delhi. And he also worked at several institutions abroad, including Vanderbilt University and the KVI University and ORNL too. Apart from this, he has been published so many papers, about 100 research papers in the International Journal of Repute. Now I would like to hand it over to the Professor Chen to start the program. Yeah, you have to moderate the right, sir. So I'm changing the desktop. Yeah, I'm just changing the laptop for this one because we are presenting his slides through the drive basically.
To share some of our excitement, what we have done in our life with all of you. And Professor Jain and Professor Alpana Goel has already created a nice background for the main theme of National Science Day in the country. That's the global science for the people, of course. And the theme of today's National Science Day here is ISA, is the role of nuclear science in emerging technologies. So without going much into all that generalities, I'll come to the main topic of my discussion here with you, is the accelerators to explore world of nuclei and particles. As Professor Unnati has mentioned, I worked in the area of cyclotrons. And of course, I got a chance also to work on the other type of accelerators in the country and to an extent elsewhere in the world. And there is a lot of excitement about these machines that we have, because these machines are probably the most useful devices with which the scientists have, in fact, explored the mysteries of atom, the nucleus, and the mysterious world of the particles. And also, they have gone to the extent of explaining what's happening in the celestial bodies and how was the universe created. There is a possibility using the accelerators to create a mini Big Bang in the lab. And maybe I'll tell you a little bit about it, because there is a lot to talk. Let me proceed further. So I will just give you a general introduction and historical perspective of this field. Evolution of different accelerator types. I'll talk a little bit about the accelerators. And I've seen your coursework, and the accelerators have been covered, and a lot of lectures are there. Basic research with accelerators, application of accelerators, and what are the future directions that you might find exciting, and then conclude. And we have another a great scientist, nuclear physicist sitting here, Professor Pancholi. He has been one of the major users of accelerators for nuclear physics research, and he has contributed to the understanding of the nuclei and nuclear models and structures, etc. Okay, very briefly, the models of atom. And the Western people claim that it's the Greeks who first said the matter is made of tiny particles which are indivisible. And it was 400 years BC. And Greeks after that didn't say much about it. But then the scientists are always curious about what's happening around us, what is there around us, this matter is made of what, and so on and so forth. And I would say that even before Greeks, our own philosophers had predicted, Kanad had predicted, even probably the Greek did, is about the atoms, that's why our we call it Parmanu and Anu and all those things. And he probably had predicted better than the Greeks, in fact. And he also told about the properties of these tiny particles. Essentially, it was same, indivisible particles. But okay, let's come back to the modern science. And John Dalton, John Dalton talked about the atoms. And what is inside the atom? Thomson made a plum pudding model. He said, okay, there is a positive fluid and the electrons are kind of, like pudding is a plum pudding, and it's a kind of, almost a uniform kind of fluid. But then, there was an experiment done. He came up with this model because he had discovered electrons. And he was trying to explain how these electrons are coming out of atom. Then, further interest was created among the scientists. Let's go deeper into atom. What exactly is this? I mean, there's definitely we are all curious about what's inside those, what is inside of anything in general, not only the atom. This atom was most attractive thing to go deeper into. Rutherford came up with this model. I come to this. He said there is a heavy nucleus or heavy center of the atom rather than this kind of plum pudding model. And there is an electron cloud, and the whole thing is huge. But then, as you know, Bohr's model came, that is most accepted. And then now there is this electron cloud model, which is quantum mechanical model of atom. Let's come back to of course, during this whole development, a lot of people have contributed to the understanding of the atom. Like Chadwick said, there is neutrons, there is a Japanese scientist, people don't talk about him much, and so on and so on. Why Rutherford? Okay, that slide is not coming. Why Rutherford said that there is a heavy nucleus? Okay, doesn't matter. I think as you know, you must have read about it. There was a gold foil experiment which Rutherford's students conducted, and there were alpha particles from the source falling on the gold foil, and some of the particles got scattered backward angles, and this could not be explained by the plum pudding model of Thomson because otherwise it will go straight. So the only thing is that there is a heavy center of the atom, and that's explained. But he wanted to know what exactly is this heavy center. So he, in fact, asked two of his students to make an experiment where we will produce energetic projectiles. So if, what is inside something, normal tendency is to break it and see what is inside. So he wanted to break that nucleus. So he asked his students, Cockcroft and Walton, two students, okay, you make a machine for me which will, create projectiles with very high energy or high velocity, and I would like to use those projectiles to hit this heavy center of the atom and see what happens. Then we will study. So his students started working on it. It was simple. So as I said, there will be an electrode floating at high potential. You will release protons here, and then from there they will get accelerated to the ground potential. They will get that energy. Potential difference multiplied by the charge. So they started off with 800 keV. That was the objective. But at that time, almost 100 years ago, it was not possible to raise the potential of any electrode or any body to 800 keV because a lot of discharges, etc., would take place. But then, while they were doing this development, George came out. He said, because of tunneling effect, at lower energies also the protons will penetrate through the atom and go to the nucleus. Because nucleus is positive, so this positive charge particles will be repelled back. So to overcome that electrostatic field, you have to give certain higher velocity or higher energy to. So he said maybe 500 keV is sufficient. So in fact, it was right. It was right. So they made this machine, and they in fact in 1932 it took them something like 4 years to make that machine. In 1932, they could produce a reaction where the protons would go and hit the nucleus, maybe, and they could see the two particles and on the scintillator. So this was Nobel Prize winning one, and they got Nobel Prize in 1951. Now I would say that this is probably the birth of accelerator, where specifically a machine was designed and invented to accelerate the projectiles to do a particular reaction experiment. So this was the first accelerator. It looks like this here. The scientist is sitting here, he is looking at the scintillation. And this is the high voltage. And today, nobody would allow us to do this kind of experiment because people were not very much aware about the damages of radiation. But then, people were so much impressed with the studies of the atom, etc. I think one Swedish scientist, he said, if you don't want to go to very high potential, 800 keV, let's have a alternating potential, which will accelerate the particles again and again. And energy is a scalar quantity, so it keeps on adding. So this kind of waveform could be used across the electrodes to accelerate the particles. Particles will keep on seeing this waveform periodically and keep on getting energy. He did not pursue this idea. There was a genius called Widrow. He was working, he's the inventor of, you can say, Betatron, another type of accelerator. He was working on his PhD thesis in Aachen in Germany, and somehow his all calculations went wrong. And his guide said, you can't submit the thesis with the kind of work which you have done. Apparently, it was not his mistake, it was a technical mistake. So in the last 3-4 months, his time was over. His guide said, you find another problem. He wrote a 27-page thesis. And he made this kind of equipment where there is a tube on which this kind of waveform is given. There is another tube here, there are gaps here, the electric field is produced here, the particles will get accelerated. Inside the tube, no acceleration. By the time it comes here, this is the potential, gets a kick again. So this is how we produce an accelerator 50K. So this is the first linear accelerator. And he got his thesis, his PhD, 27-page thesis. And you see, you should look at the date. He did it in 1928, and Indian science, same year, 1928. So our scientists also were of that high caliber and high level internationally. And C.V. Raman got a Nobel Prize for his Raman effect discovery, as elaborated by Professor Jain. And you can see big politicians visiting his labs. Today it's very difficult to get politicians to the lab. And Raman was working on other like acoustic vibration of Indian musical instruments, spectroscopic determination of structure of crystals, optics of solids, electric and magnetic properties, all kind of things. And in spite of all that, he got Nobel Prize. This is a little diversion. Coming back to accelerators. Lawrence, who was across the Atlantic. Rutherford and company were in England. So he was also working on making an accelerator to do this, nuclear, to study the nucleus. So he came up with the idea that instead of giving that, as I said, very high potential to an electrode and difficult to hold that potential. So let's use this RF again, like the previous slide. And he said, okay, let's bend the particle with the magnetic field. So it will be a compact machine. So this is how it works. There are two beams. I'm not going into details. And the potential keeps changing as the particles are getting accelerated here. And particles gain a very high energy, and then they get accelerated to high energy, and then they are taken out and for the experiments. And this happened in 1929, and it was conceived in 1932. He made a cyclotron, and he got Nobel Prize in 1939. But look at it, Cockcroft and Walton, they got the Nobel Prize only in 1951. They made the discovery before, or almost at the same time as Lawrence. So now we know there is an electrostatic type of accelerator. There is a cyclic type. It's a cyclic type, cyclotron. And it so happened is, like I said, our scientists were very active. Professor Meghnad Saha was in Kolkata again. He was very impressed with the invention of Lawrence. So he sent one of his students, V.D. Nath Chaudhary, to Lawrence's lab to learn about cyclotron. He said, we want to be at the top of the science, so let us also have cyclotron, like the Americans and the European scientists are working on kind of solving the mystery of atom. So he spent several months, I don't know, your student know about him. He eventually became the defense advisor to the government of India. He was a very prominent scientist of the Institute of Naval Physics. So a cyclotron like this was made. It so happened is that a lot of components of cyclotron were shipped from England, from USA, and during the World War they got sunk. So they had to make new components and make the machine in India. It was operating till some time back. Okay, but then if you want to go to very high energies, because the scientists are now looking for higher and higher energies, because they want deeper into the atom. And the size of the magnet becomes very large. Okay, because if you want to go to higher energies, that means either you must increase the radius of the pole, or you must increase the field. And if you want to go to higher and higher energy, because the magnetic field gets saturated, so you can't go much higher in magnetic field. So increase the size of the magnet. Once you increase the size of the magnet, it becomes very heavy, some hundreds of 200 tons. Very difficult to make that machine. So some scientists, in fact, thought about another technique. That, okay, let's use magnetic field to bend the particles and also accelerate the particles on the radio frequency electrodes. But then, as the particle energy increases, you increase the magnetic field so that they keep on circulating in the same radius. Because momentum is q/r. Q is fixed. Magnetic field also is kind of, radius is also fixed. So keep on increasing magnetic field, keep on rotating at this same orbit. And this ultimately became the one way to very, very high energies. Okay? And this is called synchrotron. This is how it works. Okay? These are the magnets and the radio frequency systems. They keep on getting accelerated, and magnets keep on bending. Some people picked up the idea of Widrow. on which he got his thesis. Because they said, okay, if you accelerate the particles using these tubes, on which at the edges we have this RF field given, as the energy increases, the tube length will be very large. It keeps on increasing. So people were scared. How long you can go if you want to go to higher energies? But then some people picked up this because it has its own advantage, the linear accelerator, because the intensities of the particle beams is very high. And some people picked it up, and one accelerator was made. It's called the drift tube LINAC in 1948 in USA after the World War. This is how it looks. Today, this linear accelerator of the TME will be very, very small. This is how it looks inside. These are the tubes to get accelerated. And it so happened is, they were all very poor at that time. So how to get these RF sources, so-called klystrons? He approached US Army. They said, okay, we'll give you 2,000 klystrons. And these were being used as amplifiers for the radar systems, the radars which were being used for the World War II. Okay, so those spare radars, 2,000 klystrons were given to him. He used only 26 klystrons. I don't know what happened to the rest. At 202 megahertz, he produced the accelerator. And this is how the linear accelerator started coming into picture. Now we have cyclotron, electrostatic accelerator, a cyclotron, a synchrotron, a linear accelerator. And basically, this is the force which governs the accelerator operation. Lorentz force is Q times electric field, Q times V cross V. This is the linear accelerator. There is no V here because it goes in straight lines. And in the case of synchrotrons and cyclotrons, this force comes from the radio frequency headroom. And this is the magnetic field. This does not give any acceleration. Acceleration only comes, this bends the particles. So this is very important. It looks very simple, but the beam dynamics of the accelerator is extremely complex. But to cut the long story short, a large number of accelerator types were developed. I'm not going into details of this. And they were used to accelerate protons, antiprotons, nuclei of atom. You strip off electrons from the atoms. So electrons from the atom, and then the bare nucleus is accelerated. Electrons, positons, missiles, and neutral particles also. We can't accelerate neutral particles, but you accelerate charged particles, hit the target, produce these neutral particles at very high energies, like neutrons and etc. And the largest accelerator complex, you all know, is the CERN, which is a complex of several accelerators in tandem. The particles start their journey here in a small machine, electron accelerator, go to a synchrotron, go to another synchrotron, go to another synchrotron. So called the Large Hadron Collider. And this is how it looks. This is almost 200 feet below the ground level. And these are the accelerators. This is the largest accelerator complex operating, and Large Hadron Collider, you already know about it. And you compare it with this little machine which other 4 students had produced. And this was happening over a period of only 80 years. That's a very small period. But then energies went from about 500 keV, that means about 500 MeV, sorry, half an MeV, to 14 keV. Huge jump, in fact, and that happened because as the scientists were demanding more and more energies, the engineers and technologists were developing more complex systems like the magnets, the radio frequency system, the vacuum system, the cryogenics, and so on and so forth. So there was a race. So development of the nuclei and particles, their knowledge, in fact, went hand in hand with the development of the accelerators. So if these accelerators were not there, probably we would not know much about what actually, is there in the nucleus or what is in the subnuclear particles. This is the longest linear accelerator, Stanford electron machine, 3 kilometers long. Just to give you an idea of what this EV and TeV and MEV you already know, but okay, one flying mosquito, its kinetic energy is about EV. Okay, so you can say, why not collide two mosquitoes and produce 2 TeV center of mass energy? You can think about it. Why did we build this huge machine called Large Hadron Collider? So think about it, why we did.
Also, size is very small.
Sorry?
Size is very small too.
Size is very small,
Yeah.
in this case. A lot of mosquitoes are around, so it's the energy density. And energy required to light a 100-watt bulb is about 8 TeV. So TeV is a very small unit, but the particles are also very small. Okay, quickly coming to the basic research that has been done. You can view accelerators also as the microscopes. You wanted to have a look at the matter, the atom, the nuclear, subnuclear particles. And these particles, projectiles which are coming from the accelerators, can be treated as waves. There is a wave nature. And as you go deeper into this, for example, atom is minus 10 meters size of nucleus is minus 14 meters, proton is minus 15 meters, electron is minus 18 meters, quarks, which now we know that it is the constituent of the protons and neutrons, minus 19. So if you want to go to deeper into the subnuclear particles, you must increase the energy, or the other way of looking at it is you want to see very small particles. So increase the energy. So the wavelength, which is associated wavelength, will also be low and lower and lower. So this is how you can. So anyway, that was just an analogy. So this is how the scientists have got in the energies. And it so happened is that from 1939 to 2009, every 3 years, one Nobel Prize came due to the work done with the help of accelerators. So you can see the importance of accelerators, the importance they have played in our understanding of the matter, the nuclear, subnuclear particles, and so on and so forth. In fact, you know about standard model of explaining the world around us, and people wanted to discover different kind of leptons and quarks and neutrinos, etc. The accelerator only have played a role in that. The latest discovery was the Higgs boson, as you know, Large Hadron Collider, and very quickly all these particles, all these discoveries, antiprotons, antineutrons, J, psi, charm quarks, CP violation, neutrinos, discovery of W and Z bosons responsible for weak interactions, top quark, one of the important quarks for the standard model, Roy-Gounon plasma, Higgs boson, charm quark. They were all discovered on the accelerators. And then, eventually the accelerator sizes became very large. For example, Levatron at Berkeley is only 6 GeV. Then alternating radiant machine at Brookhaven 33 GeV. Super proton synchrotron at CERN 100 GeV. And all these discoveries like that, in the formula 1 GeV. Relativistic heavy ion collider 200 GeV per nucleon. if you talk about gold, multiply the number of neutron in the gold with 200, a huge amount of energy. Larger than Stanford. So all these big machines made a lot of discoveries. But then, just, okay, like I said, that accelerators also help us to recreate what would have happened at the time of Big Bang, about 14 billion years ago. You have read about the Big Bang theory. So, with the help of Large Hadron Collider, because at that time there's a lot of just energy around, nothing. So after a few seconds, maybe after a second, some particles came into picture. Then there are electric forces, fundamental forces came into picture. Like that, atoms were created, nuclei were created, galaxies, stars came to our moon. So how to create a condition where there is a lot of very high energy in the system. So this is what Large Hadron Collider has done. It has created, it collides protons with protons, 70 eV energy. Very small energy is very high. So 10 to the power minus 12 seconds after the Big Bang, what kind of universe could have been existed was created by Large Hadron Collider. Okay, so this is how the accelerators help you to create mini Big Bang in the laboratory. And so now, whatever is happening in the stars, all these astrophysics studies can be done in the lab. Large Hadron Collider with its detector, and it was discovered here, the Higgs boson. And the detectors are huge, to do the experiments. The collisions take place here. One beam coming from this side, other beam coming from this side, the collisions take place here. And all these detectors which detect different kind of particles which are coming out after the collision. Whose time should I take? 10:15. Okay. India has contributed by making a photomultiplicator detector here, like here in the collision. And our scientists have contributed in various international experiments. Well, to cut the whole story short, I would say that all that we know about the atom, the nucleus, the particles, and collision of the universe has evolved over a period of time of about one century due to untiring efforts of a large number of scientists, both theoretical and experimental. Because theoreticians give the models and experimentalists verify that using accelerators. Particle accelerators have played a most important role in this process of evolution. The accelerators also evolved in this process. What I mean to say is that accelerator systems also evolved. Thanks to the ever-increasing demands of the nuclear scientists and the ingenuity of the scientists, technologists, and engineers to meet their challenges. And also, a lot of scientists work on the detector developments. So some of this probably, I'm sure, some experiments Professor Pancholi is going to discuss with you. Then, they came, so these accelerators have played such an important role in understanding of our atom nucleus and nuclear particles. But then they have also applications in common manner that we are talking about, how science is coming into the benefit of the mankind. Medical applications, Professor Dan has already told you about the proton and heavy ion therapy. And you little bit about it. Radioisotope production for cancer diagnostics, food preservation, controlling the pollution, etc. And eventually energy production, a marriage between an accelerator and a reactor would take place where we will burn all the fuel and produce no nuclear waste. and there are other applications. This is one very quickly. I'll just tell you some applications of the accelerators. Synchrotron radiation. You know, when you accelerate electrons in a synchrotron, wherever they are bending, there is an angular acceleration. And if wherever there is an angular acceleration, the charged particles emit radiation. So this was a nuisance, so-called synchrotron radiation was a nuisance because whatever energy electrons were gaining in a synchrotron, they were losing by emitting radiation. So scientists were very much fed up of this kind of thing. So they thought about linear accelerators. There is no angular acceleration. It just goes straight. No emission of radiation. But then when they studied the structure of this radiation, they found it extremely useful for basic research. So now there are several machines which have accelerators, like with accelerate electrons, they store in the synchrotron-like ring. When they emit radiation at different angles, they do all kinds of studies, physics, chemistry, biology, pharmaceuticals, materials, microelectronics, protein crystallography. There are dedicated machines to do all these kind of studies using the synchrotron radiation which is emitted, not directly the particles which have been accelerated. Just to amuse you, to keep the baby bottles dry, some scientists did some experiments to measure the water contents of super absorbent polymer materials which were developed like this, what is it called? The accelerator was used. So accelerator is everywhere. Then, accelerators, small accelerators. What I talked about basic research is huge accelerators, big ones. But they are very few in number. Small accelerators are used to produce these electronic components. You produce semiconductors by diffusion technique. That is very old now. So you, in fact, implant those materials with the help of accelerator. This is the parent material, that is silicon, and these are the implanted whatever phosphorus or whatever you want to draw. This is kind of machine, and there is a huge market of this semiconductor components which are produced using accelerators. There's another one which Professor Jain mentioned, the treatment of cancer. In 1956, Kepler at Stanford introduced a machine which he used to treat the cancer of a 2-year-old child. This was the first electronic accelerator ever used to treat a cancer. The so-called the retinoblastoma, and apparently this child was totally cured, and he survived for a long time after that. And today, that most hospitals which treat cancer have electron machines. This started off here. There are hundreds of machines, thousands of machines all over the world which are treating cancer. Of course, they are very good alternative to the cobalt-60, because cobalt-60 you have no control on the radiation. But here you have a lot of control. You can control the size of the area to be irradiated. You can control the energy of the gamma rays or those X-rays which had to fall on the patient. So this is one very major application. And Professor Jain mentioned about the hadron therapy where the protons are used, because electron or the X-rays, etc., when they enter into the patient body, they also kill healthy cells before they reach the cancerous part. So you don't want to kill the healthy cells, particularly in the case of children who are growing. These healthy cells we have to preserve at any cost, because otherwise, the children will go deficient. So the protons are very, very accurate, where you kill very little number of healthy cells, but also kill the maximum number of cancerous cells. So this is the machine. Let's say this is the cyclotron, which produces 200 MeV machine. Protons. They have taken here. They can be brought here or here or here. where the patients are lying in the, it is so-called entry, and the treatment is done, and a few irradiations and the cancer is cured. Particularly important for the brain tumors or head and neck cancers. You know, this is how the proton beam comes, and the patient lying here, and you can irradiate the patient from all directions. And there is ever increasing number of these dedicated facilities for treatment of cancers. Using proton, and hadron means heavy ions like carbon ions. And they have been steadily increasing. In 2000, they were only 14. Today, we have about 130 and more actually. And 104 in operation and under construction 62, because they have become so powerful in treating the cancers. And India has two machines. One is Apollo Chennai, the other one is in Bombay, Tata Memorial Center. It's an expensive treatment, but these days even the chemotherapy is very expensive. So doctors decide which treatment modality they should follow. Proton therapy, hadron therapy, or chemotherapy, or the combination of both. But this is one very, very important application, which is there to stay for a long time. This is one interesting application, accelerator mass spectroscopy, where you can measure in a particular sample the contents of any isotope to a great accuracy. Something like 10⁻⁻16, which is very difficult in the chemical techniques or any other technique. And this is one experiment which was done by German scientists. Because iron 60 is produced, in the Earth's atmosphere in very small quantities, and then it settles down, goes to the ocean floor, and ocean floor, it rises about 2.5 millimeters per year. Okay, and the scientists tried to do an experiment. They took samples from the ocean floor at different depths. Okay, since it is about 2.5, not per year, sorry, 2.5 mm per million year grows. So this gives you the time. They could take many samples, okay, and then they could calibrate. Okay, this is the million years, and with the help of accelerator mass spectroscopy, they could measure the iron 60 to iron contents, what was there in the sample. Okay, and they found a peak here. And this peak, in fact, signifies a supernova explosion, which took place about 2.5 million years ago, and at a distance of 33 light years. Okay, this is a very interesting experiment, and the accelerators did a wonderful role in measuring this kind of ratios. Okay. This was confirmed. In fact, by other means, it was also confirmed that there was a supernova explosion. Because in supernova, when supernova takes place, a huge quantity of iron 60 is produced. It spreads all over the cosmos, and a lot of it comes also to the Earth. And finally, this is one accelerator-driven system. Some of you already studied. I saw your coursework, where accelerators would inject beam into the reactor at assembly. You produce a lot of neutrons. In a normal reactor, neutrons in short supply. They produce power, but then they also you produce a lot of nuclear waste. If you have more neutrons, this nuclear waste production will be less, because the long-lived nuclear waste by nuclear reaction are converted into short-lived nuclear waste. So these are the kind of systems which are in the future they are going to come. So there is a marriage between accelerator and a reactor, and you have to produce very intense beam of accelerator of particles. Per protons, there would be something like 50 neutrons produced, and they would do this kind of production of nuclear power and also treatment of the nuclear waste online. Well, this is how it looks like. In 2013, there were 41,000 accelerators. They have now grown in number. And this is the first large accelerator. Only 5.5 milligram. Homi Bhabha inaugurated it in February 1962. The scientists were there. And today, we have several new accelerator centers in our country. The first one was Cyclotron Center in Kolkata, where I happened to work. There are 3 cyclotrons there. A superconducting cyclotron to go to very high levels. Inter-university accelerator centers, you all know about it. Radha Ramanna Center, this is dedicated to electron accelerators to produce synchrotron radiation for the research which I mentioned. There is a Bhabha Atomic Research Center also has accelerators at our Institute of Fundamental Research. But there are other universities who have installed small machines. But these are the major centers. And it so happened in majority of these accelerators have been built in the country. I'm coming close to my talk, end of the talk. How the accelerators have been useful for the human beings, common human beings. Some of the examples I gave you, the hadron therapy, production of semiconductor chips, medically useful isotopes, diagnostics isotopes, and so on and so forth, and eventually the power production. But then, like I mentioned, that magnets are important part of the accelerators, from very low field to very high field. So if you wanted to go to high fields, you have to make superconducting machines, superconducting accelerators, where the coil is at about 4.2 K. There are a lot of cryogenic technologies that are involved. And the fallout was, you now have a lot of MRIs, thousands of MRI, magnetic imaging, where you use superconducting machines. Levitation, which is a fusion energy. When you want to confine plasma, you use superconducting magnets. You fuse the D and T, and then produce the fusion energy. Superconducting accelerators have some magnets happening RF, radio frequency field, which give the energy to the particles, are useful for communication, telecasting, and broadcasting. Vacuum is a very important part of the accelerator, otherwise the particles don't get accelerated. Simulation, space simulation, and food processing industry. Cryogenics, I mentioned. Civil engineering. Making tunnels. For example, if you want to make a tunnel, which is 80 kilometers in circumference, how do you start? You start it, but then you have to come back to the same point within a millimeter accuracy. And so how do you control that? This is the technology developed by the accelerator community, use, coordinating measurement techniques using the satellite, etc. So all this is a fallout of the accelerator technology, which was driven by the scientists to, understand nucleus and particles. Data storage handling WWW. You all know that eventually what the internet is today is the fallout of high energy physics, where an enormous amount of data was produced. It has to be transferred to different people in the world for analysis. And so this is how the technique was discovered for WWW. And now we have the internet. Okay. This is the future. People are talking about making 30-kilometer long accelerator to collide electrons with electrons. Once again, produce Higgs boson, but it will be a very neat and clean environment so that you can measure the properties of Higgs boson, although they have been produced. Nobel Prize is there, but you want to study what are the properties. This will be a machine and many other experiments. Challenges. You see, now the accelerators have become huge. Large Hadron Collider is very big, very, very expensive. It costed almost 15 billion euro. But how long you can go? Because scientists are still demanding higher and higher energies. So there would be new new techniques by which you accelerate particles. New techniques means you have to produce higher electric fields, because electric field gives the energy to the particle. So there will be like laser wave field accelerators, plasma wave field accelerators. A lot of research is going on all over the world. Some of it in our own country. This will be a breakthrough in the accelerators. But they will also have applications. For example, a cancer treatment machine will be very compact. If you have this kind of techniques. So finally, Swami Vivekananda, more than 100 years ago, said, though an atom is invisible, unthinkable, yet in it are the whole power and potency of the universe. And with that, I close. Cynthia, thanks to the center and to all of you for your precious time. Thank you very much. I can take questions.
Now session is open for the questions. You can raise your queries to the Professor Bhandari.
कुछ भी पूछिए.
हिंदी में भी पूछ सकते हो.
Don't hesitate. Anything, please.
Good afternoon, sir. My name is Akhil Pandey and I am from Amity Institute of Aerospace Engineering. So what are the accelerator applications or innovations that you expect to be specific in aerospace industry for various students who are interested in that?
Actually, it will be the accelerator applications of the beams to measure the material properties or develop new kind of materials. So you develop special kind of material for aerospace industry. So what will be the strength of that material, or any other property which could be affected when the planes are flying, or if the cosmic rays are coming, then how they would be affected. So it will be an application of accelerator to study those kind of. This is one application I can think of.
Thank you so much.
Radiation damage is also studied.
Yes.
The electronic components when they go in the space,
Yes.
like in the huge radiation. So you have to have electronic components which are radiation hardened.
Yes.
Their accelerators are lot.
And this is a very important point. Surely, Professor Jain. Thank you very much.
Thank you so much.
All these rockets, all these space missions, as Professor mentioned, they do enormous amount of studies of radiation using accelerators on the functioning of those.
Yes.
So that would be another application. Thank you very much.
Sir, my name is Tushar, and I wanted to ask you, you discussed about ETS.
Sorry?
ADS.
You discussed about ETS.
Mm-hmm.
So, now, India has a large reserve of thorium, right? So, the only problem is that the current is low, peak current is low, and we can't operate our accelerator system for a longer time. What do you think? How much time is left that we can derive a ADS system for thorium plant?
You see, it's a very good question. Probably you know that for thorium we have a 3-stage nuclear power program. Okay, but then the accelerators have shown some promise there, where you can convert thorium into uranium-233, right? But then the technology of accelerators to make those kind of beams available, where so-called 10 or 50 milliamperes of proton beams at 1 GeV, and at the same time, the reliability of that means they have to be highly reliable. You can't afford the accelerator to break down, and to high beam currents, the materials, for example, which will allow the accelerator components to accelerate those kind of high intensity beams. Suppose there is a slight shift in the beam, then the beam will go hit in somewhere, and with megawatts of power, it will just punch a hole through. So those are the technologies which people are still working on. And the first one I would say will be from Belgium. Some results will come where they have already made this kind of system, a very intense linear accelerator, which will inject beam into the reactor. We should get the results very soon. But that is it's a demonstrative kind of thing. But to make it in a commercial scale, I would say it will be a lot of time and a lot of investment. But scientists it has been understood that it has potential, because fusion has been going on for a long time. Every time you say when the fusion energy will come, people say 50 years. 50 years ago also they said 50 years. But it's making progress. But these are techniques which are more under control, and maybe 50 years, I don't know. But okay, people are working very seriously.
So let's thanks to the speaker. Thank you, sir, for giving huge knowledge to our students. Now I would like to invite you, Professor Suresh Pancholi, for discovering the nuclei using the accelerator, which is an example, the 1858 ER. Sir, please.
Thank you, Dr. Unnati, for the kind words. I would like to thank Professor Alpna Goyal, Professor Jain, to invite me here. This is my first visit, and I'm impressed by the developing setups in the labs that they are there. I'm used to, in the classroom, experiments which are, or the instrumentation for the experiments which are so simple, but now with the advancement in electronics and other technical things, the experiments have become very nice. In small space, you can have the same things that which you could do earlier with bigger setups. One thing that I am impressed here is about the application part of nuclear science, nuclear security. I think there's a lot of room in developing such systems. Well, coming back to what I want to say here, after a beautiful talk by Dr. Bhandari, who is a great expert, as you all know, in accelerator sciences, I have very little to say, but before that, I would like to say something. Professor Jain mentioned that even before getting the Nobel Prize, Professor Raman booked his ticket. But where to? For the students. Does anybody know where? Where do you get the Nobel Prize?
Switzerland. In Switzerland.
Every year in Stockholm, every year, December 10th, there is a ceremony in Stockholm where the King of Sweden confers the Nobel Prize on the Nobel Prize winner. Something like 62 years back, I had the opportunity to attend one of the Nobel Prize ceremonies in Stockholm. At the time, R.L. Mossbauer from Germany got the Nobel Prize for the recoilless emission and absorption of gamma rays. And that's an impressive ceremony to see that. Just I thought that in continuation with what Professor Jain said, I complete the journey part. Okay, coming back to the lecture, with all the details explained so very beautifully by Dr. Bhandari, I cannot take a leaf out of his lecture and talk about it. I just want to take a point out of it because there's lunch time that you are waiting for. So I'll take about 10-15 minutes only. The important role of accelerators in nuclear physics research. What the accelerators contributed for nuclear physics research in the beginning. The usual method to study nuclear structure physics, that means study of nuclei. At that time, before 1970 or so, was done by using radioactive sources like you are using cobalt-60, cesium, and 137, and so on, and to study the decay of it, beta decay taking place, gamma decay taking place. With the advent of the accelerators, one could, by nuclear reactions, excite nuclei at much higher excitation energies than the energy available in radioactive decay. So I am going to describe to you by taking an example of erbium-158 nucleus. It has the proton number 68 and neutron number 90. I have taken this example, classroom example as it is called, to show the importance of accelerators in nuclear physics research, as I said. Where is it? Up in the, I see. Okay. This nucleus can be populated by a nuclear reaction, which the reaction disappeared. Okay. By using oxygen-16 beam from an accelerator, like the accelerator which is at IUAC, Inter-University Accelerator Center in New Delhi. The reaction used this oxygen-16 beam at an energy of 84 MeV on a neodymium-146 target. This can be done at IUAC with, after the reactions, the gamma rays that are produced, they are detected in these detectors. These are detectors in front. These are only liquid nitrogen receivers because the detectors, the germanium detectors work at liquid nitrogen temperature. It's a spherical arrangement of detectors, maybe 14 or 18 such detectors which are known as the Clover detectors. And the beam comes, for example, this way, at the center. At the center is the neodymium-146 target. So from the target, gamma rays are emitted after the nuclear reaction. And those gamma rays of different energies, ranging from, let's say, 100 keV to, let's say, 1.5 MeV or so.
Next.
Yeah, the Clover detectors, that array that I showed, one of the Clover detectors is shown in this photograph. The detectors are right in front. As I said, this is the liquid nitrogen fever. The detectors are 4 germanium detectors. And these detectors are Compton suppressed by surrounding it with another scintillator. The other scintillator is bismuth germanate. Bismuth germanate crystals. So this is the germanium detector and surrounded by the bismuth germanate scintillator. And the source is in front.
The next.
I come in between the audience. What kind of gamma ray spectrum that is produced by such a detector? As you already know, cobalt-60 gamma rays, they are 1173 keV and 1332 keV. It is followed by beta detection. So here is the gamma ray spectrum. The two full energy peaks are at least 1173, 1332, and at lower energy is the Compton distribution. I hope you know very well what the mechanism of detection, the three processes, Compton scattering, photoelectric Compton scattering, and wave production. I need not go into the details of that. So this is the Compton distribution, but by surrounding the therminium crystal with another scintillator in such a manner that you can get rid of the partial energy events and try to get only the full energy events. So this bottom one is the Compton suppressed, where the Compton is so much lower. Compton distribution is so much lower in number. So you have only the full energy peaks. This is just a simple spectrum, but what happens if you have not only two gamma rays, but many more gamma rays? Then such distributions would overlap. The Comptons would overlap. The Compton would rise substantially. So there is then a need to do the Compton suppression so that you can get full energy peaks there. You can find their intensities, you can find their energies, and so on. So in the population of Erbium-158, by one of the nuclear reactions that I showed, this can be populated using several nuclear reactions. So in one of such experiments, the gamma ray spectrum was taken with a suppression of the background. The background is here suppressed. So it's a very low. Otherwise, this would be all there, and some of the smaller peaks would be submerged in the background. So with Compton suppression, you get a spectrum like this. These are the full energy peaks of various. And how do you make a level scheme out of that? By measuring the singles energy and intensities and coincidence relationships, time relationships. You come out with a level scheme of this type. Why a level scheme of this type? Why not a haphazard level scheme? I'm using the word haphazard because if you take nuclei of different types, spherical nuclei or deformed nuclei, you get a pattern of a decay of levels in this form. I have not shown the higher one here, but I can go to the higher one also. This is from another experiment. This scheme is from another experiment that is using tin 122 as the target and argon-40 as the beam. The charged particle beam at 182 MeV in this particular experiment. This experiment was done in Belgium using a cyclotron. Now, what is the charm and beauty of this kind of spectrum? From theoretical considerations, I'll come to that a little bit of that. That we expect that this spectrum should go just like this. From theoretical consideration, the energy, excitation energy increase or gamma ray energy increasing should have a certain relation. What is known as the I into I plus 1 rule. But what happened in this particular observation? That there was a discontinuity. There was an abnormality in the gamma ray spectrum here. This is the plot of spin versus gamma ray energy. So one discontinuity was observed between spin 12 plus and 16 plus. Then there was another discontinuity observed at spin 26 upwards. These two observations were turning point in study of nuclear structure. And at the time, when I mentioned about time, for such discontinuity at lower energy that was observed in atmosphere 160 using this particular relation, and that experiment was done in 1971 at Stockholm using the 225 centimeter Stockholm cyclotron. That was in the year 1971. At the time, there was a lot of excitement about why this discontinuity has come. Theoreticians came to help and said, this nucleus, Admium-158, the property of which I just showed. This is a plot of energy. I showed gamma spectrum with the first excited level 2 plus, second excited 4 plus 6%, and so on. So if you plot the energy of the 4 plus level to the first 2 plus level, as a function of neutron number, you find these kinds of curves. For erbium nuclei, green one and so on, deuterium, hafnium, and for erbium, I said for erbium 158, neutron number is 90. So if you look at 90, this is the point. So the ratio is 2.74. And what is the quadrupole deformation at this? You can find out quadrupole deformation from, for example, basically the 2 plus lifetimes of the 2 plus level. Lifetime of the 2 plus level. 0.27. This one is when the nucleus is vibrational type. This is when the nucleus is completely rotational, rigid rotational. What is the value of this ratio? 3.33. So this is in the transitional region. So one can also expect the rotational behavior. And if you get the rotational behavior as expected from theoretical considerations, those abnormalities should not have come. Why did such abnormalities came? Is because at a certain rotational frequency or excitation energy or spin value, the high J neutrons in this particular case, I13.5 neutrons, they decouple from the core. I'm not going into the details, and they start spinning with their angular momentum aligned along the rotation axis. When such a phenomenon takes place, then you get a discontinuity and a jump in the angular momentum rate. Not going too much into the details of the experiment, but I must mention that at a higher excitation energy also there was a discontinuity obtained, but that was due to the rotational alignment of H11.5 protons. So this phenomenon takes place at different excitation energies. Actually, this discovery was one of the basic points in turning points in high spin nuclear physics. And there was a reverse flow also, was that how to develop heavy ion accelerators so that one could study nuclei at higher excitation energies and angular momentum. Here in this particular figure, the black points or the black line, it is called the line of beta stability. On the left of it are the neutrons. This is the plot of Z versus L. On the left of it are the neutron deficient nuclei. And on the right are the neutron rich nuclei. So a lot of investigations have been done throughout the nuclear chart on the neutron deficient side, but not very much on the neutron rich side. The reason being that nuclear reactions have the target and the projectile both stable ones. Stable target, stable beam. But with the advent of other reactions and radioactive ion beams and other sophistications, or by sophistications I mean, like for example, studying Coulomb excitation and other types of investigators, one could study the neutron rich side also. So there is a lot of scope in the study of the greener part. A lot has been investigated, a lot still needs to be investigated. During the last 4 or 5 decades, many interesting phenomena were observed on the left side for the neutron deficient nuclei. For example, super deformation, magnetic rotation, anti-magnetic rotation. Professor Jain is a pioneer in this field. He has done a lot of work in these phenomena that I just mentioned. In this, I tried to emphasize to you that, well, thank you has come before. Through an example, I just wanted to emphasize that the role of accelerators in nuclear physics is very important. It will remain so in the investigation of nuclei on both sides. This is one particular type of application in nuclear physics. There are many, many others as Dr. Bhandari explained. So one could summarize and say that accelerators for knowledge, not only in nuclear physics, but many other fields. So I'll just stop here.
Session is open for the question. So if you have some queries, then you can ask to the sir.
Very expensive accelerators are being built for this kind of
Research.
very expensive accelerators are being built for the studies that you mentioned, using the radioactive ion.
Yes.
They offer a lot of challenges to these young people using those machines. Yes, sorry.
Questions, please.
Although I have not gone into the details of nuclear models or other aspects of it, and Professor Jain is here and several of the staff members can explain to you some of the basics. The time was not enough for me to go to that.
So there is no query. So let's thank to the Now this session is ended. So proceeding the program. We are proceeding the program, and there is for the proceeding what we have done. We have organized 2 activities for the students. for the NST students. One is the cancer awareness program. Another one is the harmonic, which is Parmanu Ki Sargam. So today we are announcing the awards for the awareness program. For that program, we invited some write-ups from the students. So we have selected some best from among them, and then we would like to appreciate our students what they have written in their languages. Certificates. Ma'am, sir. So now I would like to invite Professor Goel to give the certificates for the students.
Which we are using daily, and the alternatives. So this is very nicely.
So let us announce the result.
Madam, are you there? Can you
I will start from the third one. I would just start with the third one. Yeah. So third one is getting Brijesh Kumar.
Vijay बताएगा, आज ये
Vijay,
बताएगा क्या बताएगा क्या
first tell what you have done.
The radiation type of RCT cancer because
Speak loudly.
in carcinoma topic I would discuss a very problem related issue how to reduce the carcinoma to cause the cancer reason. So I will focus on the protect yourself from the sun. Sun body radiation will everybody know that. In the avoid the midnight, the time is 10 a.m. to 4 p.m. This time is for midday sun. There is a lot of we said that radiation is very high for the sun. That is why we avoid to go outside to 10 to 4 p.m. And next day stay in the shadow. Maybe we will outside in Delhi. We said there are a lot of hotels. So we keep in the shadow so that we can protect ourselves. And cover your skins. This is a very important task. Then don't use a tablet using. Some people using tablets to moisturize skins, and we have to avoid. So this topic I have discussed in the
It is not clear me. Which type of the tablet they are using?
I don't know the exact name, but people will use it.
How they use the tablet?
They protect from the sun. They like
They put some
Sunscreen.
Okay. So let us have a
Big clapping for
Gordon.
Brijesh Kumar.
Congratulations.
So our next prize goes to,
Congratulations.
second prize goes to Muhammad Tabish. So Tabish, come here to collect your certificate. And a big clapping for him too.
what you have written?
So the thing which I have written in this report that I made is basically how the thing which you are consuming, you have to aware about that. Okay, and the main what you are eating, what you are applying on your skin, what you are basically consuming, you have to know about every single chemical composition about that. So whatever comes to you, it will get entered and it will get affected immensely into your skin. So it might later cause a cancer and any sort of deformity in your body or somewhere in your body. So the first thing that I mentioned is this, and related to that, it is basically at the same time the same precautions that I mentioned just now. They are covered with that category. And that's all I just
Okay.
mentioned.
Okay, thanks. Clapping for Tabish. Now the first,
You mentioned about the skin cancers.
Basically,
Just
any
one-
sort of thing that we are applying on our skin. You
No,
have
what I want to say, one interesting fact is that Lawrence, who invented cyclotron, used his machine to produce neutrons, and they were used to treat the cancer of his mother's skin.
Okay.
So this, discovery, all these scientists, when they used to make this, even their own relatives, they used to make guinea pigs. But it was treated, his mother's. She was cured. She was cured.
Using the neutrons, the cancer is
Yeah.
cured.
Yeah.
So a big clapping for the Arham. He got the prize. As
So
more.
I basically laid out the 5 of the most common carcinogens that we encounter in our environment, and I explained the causes of and effects of those carcinogens on our body. The effects, of course, include cancer. That's the most common one. But like the carcinogen that is in tobacco that we smoking, so that might cause the damage to our lungs. So I then gave the alternative for that. That could be quitting smoking altogether, of course, or you could get nicotine patches. And the other carcinogen I described was asbestos. Asbestos is a naturally occurring mineral that's found in insulators or building materials. So we could use alternatives like cellulose or fiberglass instead of that. So that could reduce the risk. And just like that, I described others like pesticides or formaldehyde. They are great carcinogens. And of course, UV radiation that explained. So that's what I did in my.
Sir, I would like to add here that he is our first year student. Still, he has not studied about the nuclear science. He is still in the just basic paper. He is in the course, but he has courage to present this work here.
Yeah.
That is, I think,
More
that is,
appreciated.
we should appreciate the courage he has. Confidence. This is for you.
About the second activity, we students submitted their posters, but yes, so I would like to show them. Mouse. चार्जर मेरा कहाँ गया चार्जर लेके Are you sharing or I'm sharing? ये Zoom का स्क्रीन है This is a Zoom screen.
Not in particular order, so जिसका आ जाए poster please वो explain कर देना. So would you like to explain?
This is one of the posters sent by the Sohail. These are 6th semester students of BTech MTech integrated program. मैम बड़ा करिए थोड़ा सा फुल स्क्रीन.
Tell about yourself, in which course, which you are going, and then tell about your.
Good afternoon, everyone. My name is Shohei, and I'm 6th sem, Computer Science and Technology. I'm an integrated student, BTech plus MTech, and this was my poster. So basically, the topic was harmony in nuclear energy. So like even I didn't know like what were the applications before coming here of nuclear energy. So like after coming here, I've gained the knowledge of like how it can be useful to us. Uh, it is harmful, and if we learn how to use it, we can change it to what our purpose.
Yeah, here, what's that? Can you explain? You know, radioactive symbol becomes a
Found it somewhere.
Ma'am, next one. Thanks to the Ma'am, next one. Some student had also designed himself. He has found it. He submitted last moment today itself. One of the student has been made a poster by hand. It is one corner is incompleted, but today is someone has shown. Yeah, he has designed very big poster and a very good too. Shreya.
Good afternoon, everyone. I'm Shreya Singh. I'm in 6th semester. So our topic was to explain like how nuclear is not just about war, and it is also useful for our society. So in this poster, I basically explained like how nuclear energy is is a kind of renewable or sustainable energy source. So we can just use it as a replacement of like coal energy or like any other sources we are using currently to produce electricity. So it would be like good for our environment, and it would be like it would not that harmful for the
Painting you made it.
No, sir, I just downloaded it.
Downloaded it and showed. Sorry.
You see, we have, sorry to interrupt.
Sir, your poster is designed by originally by me.
No, what I
Yeah.
want to say,
Yeah.
we picked up a very interesting
Yeah.
topic. Somebody has done a calculation, the thorium that we have in
Yes.
our country. If that we convert into uranium-233 and of this three-stage nuclear program, it can meet our requirement for power for next 500 years.
500, up to the 500 years. Only
nuclear using that thorium. 500 years. This is really very, very powerful topic.
So it was a query, I think, raised by this Tushar.
Yeah.
Yeah. So next poster, ma'am. So whatever the requirement right now, we can based on that we are saying, or the increase of the requirement of the power.
Increase requirement. It has been projected.
Yeah, right. So, because nowadays the all electrical vehicles are there, electrical cars and the electrical other things.
As we are making progress, what will be the capital consumption?
Combustion energy will be.
That kind of projections have been made.
Right. Next poster. Brajesh Kumar.
The topic is clear that there is application of the nuclear energy. Our aim is that the atom for peace, to say no to wars, nuclear wars. There is a lot of things happen beyond the nuclear energy we use. Nowadays, we say that nuclear energy is used for the nuclear medicines. Already discussed the Molybdenum technetium we will use that. In the agriculture, this is a major role nowadays in nuclear application to store a food for a longer period of times. And industrial things like accelerator we will have now will discuss. They're very beautifully explained by the scientists of here. And now we say that there is also I don't know the exact word, but Pluto is also found by the nuclear techniques, by the nuclear technique methods. And
Pluto.
When Pluto, I read it from the internet. Pluto is found out by the nuclear technique.
प्लूटो खो गया था, उसको ढूंढा, गुम हो गया होगा ना, उसको ढूंढा होगा न्यूक्लियर टेक्निक मेथड से.
And all of the millions of application I have discussed, say no to war, nuclear wars, then we will use the nuclear energy in the other part of this problem. Thank you.
The next poster. This is Nidhi. This is designed by you? Yeah.
Good afternoon. My name is Nidhi Pandey and I'm a fourth semester student. So here I have highlighted the topic nuclear is not just about wars and bombs, so that common people, they can understand the fact that nuclear doesn't mean destruction only. And it is way more important and useful for us. So here I have only mentioned two most major aspects of the nuclear energy. First is carbon-free energy, and according to IEA.org, I read a data over there that nuclear energy has reduced, over the past 50 years, it has reduced the carbon emission by 60 gigatons, and that is a lot. And it is safer and cost-effective. Why safer? Because it doesn't create the byproduct that is byproduct, the harmful byproducts that come from coal, oil, etc. So it is way safer and effective, and it is a carbon-free energy, and it has a lot of scope.
So this poster is the original one. Next, एक और है. Trishu, पतंग उड़ाई. Kites are flying. Reactor bomb. This is a bomb.
Very artistic bomb.
Shall explain, karo.
Nuclear is not just only bombs and wars, but we can use this energy for the welfare for the society. We can.
So you have somehow entangled the bomb with the threads.
We can make the energy for the good cause, not for the destruction. But I also like the use of the bomb.
Oh, good.
You like the use of bomb.
नहीं? क्या करोगे उसका?
Test
it.
You see, deterrence is the next. He just wants to test it and keep it with himself, like everybody else is doing.
Right. I think one more is there.
You can do all the simulations on the computer.
Right.
No, I want to see.
So you will convert that bomb into the flying the kites or in the pigeons? Right. Okay. Okay. Thank you. The last one. No, one more is there. Yeah. This is the second last.
I've already shared now.
The thunder is second last.
Shubhashish.
Primarily, the topic is to present and.
Your name, please.
My name is.
A bit louder, please.
My name is Subhashi Shah.
Subhashi Shah. And the which class?
I'm from second semester.
Yes. BTMT program or BT program?
BTech.
BTech. Right. Now start.
Primarily, the poster hangs around with the
what the current situation of many states of an Indian foreign related to food stands around, and through the nuclear technology, the scientists could making variants of the specific food crop much more what to say enhanced and short span of time, first to experiment with one nutrient contribution.
They are faster grow and higher in yield. Faster in grow and higher in yield, right? Okay. So thanks to the Bhaji for your question. The last one, ma'am. There are more. You received the entries. Okay. Who is that? Fine.
Give your introduction first.
तो जो केंद्र विज्ञान है, जो न्यूक्लियर साइंस है, वो उसको हमें डिफेंस के लिए यूज करना है या फिर किसी पर्पस के लिए यूज करना है। पर जैसे आप रशिया देश है जो यूक्रेन को डराने के लिए अपना सुप्रीमेसी दिखाना चाहता है, वैसा नहीं करना चाहिए। वही है।
Who is that? Tavish. Sujal. This one.
He was the first person to send the poster.
My name is Arab Jared. I'm a first year student here at IIMSP. So I designed my poster on the various applications of nuclear science, except for defense or the bomb-related research discussed. So like here I placed the nuclear power. That's our global, the global warming issue that can be solved with if we use nuclear power. Then I have used here nuclear medicine that Sir has discussed. And here the research purposes, that accelerator one, that I have combined all of it in my poster. That's what.
This you made yourself?
This one.
This is originally
like the prompt is AI generated. Then I took I used this design and all that.
The placement of the different cut and paste type of things. So it's okay. Good. Thank you. सर लास्ट में एंट्रीज आई हैं सर बैठे बैठे भी कुछ नहीं मैं जो वो लास्ट पोस्टर इतना मुझे उम्मीद नहीं थी लास्ट में पोस्टर में बच्चों ने दिस इज द लास्ट वन एंट्री
Basically, this is the journey that I wanted to show you, starting from research to the nuclear energy to the application based on nuclear energy. So most of the things have already been explained by the students and even this, about the research has also been explained. The things that are based on the nuclear phenomena, even the structural analysis of the cosmological deformed nuclei. So I just wanted to focus on these application points. And how does these applications that are based on the nuclear phenomena are helpful for us to getting more advanced into that technology. So this is something which I want to show you.
Thank you, Ramesh. Now this session is over. We are not giving any participation certificate or for this event, basically poster, which we have organized on the with the message that the nuclear is not just war and bombs. So harmony of the atom, which is harmonics. So because few entries are left, they could not prepare their posters. So after a few times, we will select the best from them and we'll announce the poster certificates. Right now, ma'am, for this, I would like to ask that ceremony. Yes, I'm good. So now we would like to go towards the felicitation of the Professor Bhandari and the Professor Pancholi. So, ma'am, felicitate.
Please. Sir. Yes. We all have gained so much. आपकी विजिट होना हमारे लिए बहुत बड़ी बात है.
एक ग्रुप फोटोग्राफ के लिए
ग्रुप फोटो आ जाओ.
मैं वोट ऑफ थैंक कर दूं सर.
ये थॉट्स में फोटो देखो.
एक फोटो सब लोग आ जाओ.
आ जाओ.
उधर सुरेंद्र को बुलाओ.
सब लोग आ जाओ.
So in meanwhile, the students are collecting. I am giving the vote of thanks to our on behalf of the entire program. I am utilizing the time. So I am thanking to all entire honorable founder, president, and Dr. Ashok K. Chauhan. And I also thanking the Chancellor, Dr. Atul K. Chauhan sir, and the Vice Chancellor, Dr. Balvinder Shukla madam, for providing the necessary support for the program. And I also thanks to the today's speakers. First, I would like to thank the Professor R.K. Bhandari for taking off us for a long journey of accelerators, and Professor S.C. Pancholi. We explore the nuclei with the how we can explore the nuclei with the accelerators. He gives the view of that. And then I would like to express my deepest gratitude and appreciation to all the people and organization who have made this event huge success. Thank you for all.
आगे कोई यार मैं तो देख लिया.
Thank you.
Thank you.
Thank you sir. Thank you so much. आज हम लोग सब बहुत कुछ सीख लिया है.
Thank you.
सर हम लोग कितने दिन से वेट कर रहे थे. हम लोग आएंगे. बहुत बेसिक चीजें हमने सब ऐसे कवर करा.
सेलिब्रेशन है. सेलिब्रेशन. आप लोग यार इतना बड़ा सेलिब्रेशन हो गया.
जी सर, थैंक यू सर. क्लोज कर दीजिए. Now thanks to the IT team को thanks.
Thank you all. I hope you all enjoyed. And still, if you have any questions, if you can write, send it to us, send it to us. Okay? So that you can have your here. Right? And congratulations each one of you who has contributed in the poster session or in the essay writing.